Yep. So when we usually think of particle detection in the context of interacting with some kind of external field, we usually mean some kind of quantum matter system with discrete energy levels, which can undergo discrete transitions between those energy levels due to the emission or absorption of one single quanta of energy. So in the photoelectric case, this would be the emission or absorption of single photons. So these kind of photon detection processes were really key in the formulation of quantum theory in the early 1900s, such as the Bohr model, which models the emission or absorption of single photons in bound states of atoms, or the photoelectric effect, which works off exactly the same principle, but rather than transitions between bound states of an atom, you have transitions to a continuum of excited states. And it's worth really highlighting here that the original studies of these photon detection processes were not single photon input. They were stimulated processes where the detector interacted with a coherent state of high amplitude consisting of many, many photons. So we really the main question we set out to answer in this project was, can we observe a detection process of that kind for the interaction between gravitational waves and quantum matter? And the conventional answer to this question is no. So Dyson famously did an analysis about whether it's possible to detect a single graviton, and he reached the answer no for two main reasons. Firstly, he really had this concept that a proper detection is only a detection when there's a single graviton input to the detector. And he was also only considering these processes for atoms. So Weinberg did calculations on the rate at which an atom emits and absorbs gravitons from the gravitational field vacuum, and he reached the answer of 10 to the minus 40 hertz. So needless to say, there's no chance of ever detecting that kind of transition. But quantum mechanics is no longer limited to just atoms. We can prepare quantum systems prepare massive systems in quantum states at really macroscopic mass scales. For example, the kilogram scale LIGO mirror has been prepared close to its quantum ground state. So fueled by that motivation about increasing quantum control over massive systems, we revisited this question and reached the contradictory answer of yes. And so the way we reach that answer is by really looking at these stimulated processes, or the gravitational analog of the photoelectric effect. And the key insight which enables us to overturn this answer is that you don't really need a single graviton input to infer the exchange of single energy quanta between matter and gravitational waves, which is exactly what occurs in the photoelectric effect. And then if you use, rather than an atom, a massive quantum system, for example, a Weber bar, so a Weber bar which has quantized acoustic oscillations, so either the Weber bar is if you have some continuous energy measurement of its energy levels, the Weber bar is either in its ground state, and if some force drives it, then it will jump between its quantized energy levels. And so then if the driving force is a gravitational wave, when you see a click in the detector or the Weber bar transition to the n equals 1 Fock state, that corresponds to the absorption of one single graviton from the field. And that is exactly a gravitational version of the photoelectric effect. So the reason this is possible with Weber bars is because Weber bars provide a macroscopic enhancement for the interaction between gravitational waves and quantum matter as compared to the case where the matter is an atom. The Weber bar has, I won't go into the details because it's in the paper and also studied to death in the literature. But basically the Weber bar's mass scales with the number of atoms that are vibrating in the Weber bar. And this provides an enhancement with the mass of the system, which enables this rate that I was showing you before about the interaction with the gravitational field vacuum to be enhanced if we use a Weber bar instead of an atom. So say we prepare the Weber bar in the n equals 1 Fock state, then the rate at which a single phonon will be annihilated and a single graviton will be created in the gravitational field vacuum is 10 to the minus 33 hertz. So this is orders of magnitude better than the rate for a single atom, but still vanishingly small. So we won't be able to detect this transition. But now if we look at simulated emission and absorption, so we look at a Weber bar close to what Joseph Weber had prepared and a strain amplitude close to what LIGO has detected, and we obtain 1 hertz. So this really brings close to reality the possibility of witnessing the exchange of single gravitons between a gravitational wave and quantum matter in a controlled earthbound experiment. So, however, this rate that I just showed you assumed resonance over a long duration. Assumed resonance over a long duration. It was calculated using Fermi's golden rule, which is a really crude approximation. The detected gravitational waves by LIGO chirp, as well as suspected sources of high-frequency gravitational waves, primordial black-hole mergers, are also expected to have a frequency chirp. So we really need to account for the time variation in the frequency and strain amplitude. So when we account for this in the model, we explicitly accounted for this in our model, and we found that the response of, say, a bar to a chirping gravitational wave of chirp mass 10 to the minus 4 solar masses, and say a rare event with strain amplitude 10 to the minus 16, the bar detector parameters required to witness the exchange of one single graviton between field and matter are close to what has been achieved in current lab experiments.
Sorry.
But
since you made this specific estimate here for a primordial black hole merger, does this estimate take into account the duration of the event as compared to the ring-up time of the bar, or is this assuming you have that signal coherent over an extended period of time?
So it's just a chirping pulse. So you have a ground state called Weber bar, and you have a chirping pulse, and it's just such that the signal or the rate of phonon generated by that chirping pulse is greater than the thermal generation of phonons.
I see. Okay.
Yeah.
Thanks.
So we really wanted to shoot for the gold medal in this project. So because we don't know if sources exist in that high frequency range, but we know with 100% certainty that sources exist in the LIGO band of gravitational waves. We have detected them. So if we can get the detector to work in this frequency range, we know with 100% certainty we'll be able to see a signal. We'll be able to do a gravitational version of the photoelectric effect. So we focused primarily on frequencies in the LIGO band and looked at the detector parameters to witness the exchange of one single graviton between the gravitational wave and the quantum matter. And it was surprisingly not that far off what has been achieved in the 90s, in one of the last times that bars were in real active use for gravitational wave detection. So these parameters, I don't have time to go through them in detail, but they're calculated so that the signal from the gravitational wave is you ground state cool the Weber bar, and these are the parameters so that the signal from the gravitational wave is larger than the thermal noise. And they're really not that different from what they had in the 90s. So that's exciting, but one thing I'm neglecting to mention is that to really make a gravitational analog of the photoelectric effect, it's not enough just to detect a gravitational wave. You really need quantum sensing or quantum jumps between discrete energy levels of the Weber bar. So here, Srinath, my collaborator on this project, who is also in the audience, simulated the continuous measurement of the energy levels of Weber bar, say a ground state called Weber bar, and in the red window there we've got a 4.4 second chirping gravitational wave pulse incident on the bar. And in this run of the simulation, the Weber bar, the continuous energy measurement projects the Weber bar into its n=1 Fock state. And this provides a direct gravitophononic analog of the photoelectric case where a single photon is absorbed and the atom undergoes a transition to its excited state. Whereas in our case, a single graviton is absorbed and the Weber bar transitions to its n=1 Fock state. So what has been achieved in terms of the quantum sensing side, so the largest masses which have had this kind of direct quantum sensing of individual energy levels are on the order of microgram masses. So that's still orders of magnitude away from the kilogram scale that we need. But what has now been achieved is orders of magnitude better than the atom, which is what previously we were only able to do these kind of experiments for. So a lot of progress is being made in the right direction, and also in other systems doing continuous measurement of massive mechanical systems. So hopefully I've convinced you that this experiment is not impossible, but what would it mean if we actually did it in terms of providing evidence for gravitons or the quantum nature of gravity? So the three archetypal signatures of the photoelectric effect that we all remember are the threshold frequency, the independence of the ejected photoelectron energy from the classical electrical field intensity, and the near-instantaneous ejection of photoelectrons. In the gravitophononic setup that we have here, we have all these three signatures. We have a threshold frequency, so the phonons are only produced when the gravitational wave reaches a certain threshold frequency. The phonon energies that are produced are independent from the gravitational wave amplitude. And the timescale for the gravitophonon production is the measurement strength. So the measurement strength is the timescale that it takes your continuous measurement to project the system into the n=1 Fock state. And that provides the analog for the timescale at which photoelectrons are produced in the photoelectric effect. So the caveat here is that, okay, Einstein explained the photoelectric effect in terms of photons in 1905, but many years later, others came up with semi-classical models which can also explain the photoelectric effect without quantizing the electromagnetic field. An example of this is the Rabi model, which many of us learned in undergraduate physics, which can explain transitions in atoms without quantizing the electromagnetic field. However, the caveat there is that these semi-classical models, must violate energy conservation for single discrete transitions in energy. Being that if you see a discrete click or a quantum jump in energy on the matter side, if you believe in energy conservation, you must have a discrete click or a quantum jump by h bar omega on the field side as well. And if you have those stochastic quantum jumps in energy, that is inconsistent with the Maxwell equations in the electromagnetic case. And that was the whole point of the photoelectric effect originally, is that the reason it provided evidence, the first evidence of photons, was because it provided an experimental outcome which is inconsistent with the classical Maxwell equations. So in this case, the conclusion you could reach is that if you believe in energy conservation, the experiment is inconsistent with the gravitational field treated as a classical continuous wave that solves the linearized Einstein equations. Now, many years later, quantum opticians came up with a higher bar for what defines a photon. These experiments of the 70s and the 80s, Hong-Mandel effect, negative subpoison statistics. So in my view, these really close loopholes on the existence of photons in that they really rule out these semi-classical alternatives. But it doesn't take away from the fact that these early 1900s experiments involving the photoelectric effect really provided the first evidence of the existence of photons by providing an experimental outcome which was inconsistent with the Maxwell equations. Thank you.
Okay, thank you very much. We have time for questions. I can actually maybe start with a question. So you mentioned one has to show that there is a threshold. So how would you do that? Because you can't turn on and off the light switch.
So that's where LIGO comes in. So LIGO is essentially your source control. It tells you when a gravitational wave is there, what its frequency is, what its strain amplitude is. So yeah.
So, yes, there's a question in the back. Yes, please.
Yeah, I was wondering, with the niobium detectors, was there any detection of this gravitoelectric effect, or did they see any extra phonons exciting from whatever neutron stars might have been merging when those detectors were on?
So I believe the issue there is they hadn't ground state cooled them yet. In these calculations, we assumed that the Weber bar was ground state cooled and just looked at the parameters for which there would be a signal would be seen. But what our calculations were showing is that if back then they had ground state cooled them, they would have detected these neutron star motions.
Right. So in the photoelectric effect, you don't ground state cool the metal, right? You still see an extra current in the metal despite on top of its thermal electrons, right?
Well, no, the atoms that are in the metal from which electrons are ejected are in their ground state. All you need is a transition between, well, no, they might not necessarily be in their ground state, but they're in a quantum energy level, one of the discrete energy levels, and there's a discrete transition between quantized energy levels to a continuum of excited states. And so it's really that discrete transition which is the core of the photoelectric effect.
Maybe if I could follow up on that. I mean, I guess you would also need the ability to detect single phonons in those Weber bars, right, which does not exist. So.
Okay. Yep.
We knew when we were building the Weber bars that we could have maybe, I don't know, 10,000 phonons, but we could be sensitive to one added phonon, so between 10,000 and 10,001. Can I do that? Would that work? Because then we don't need to ground state cool. All we need to do is have your noise, the way you measure the noise, like because it's high Q and you measure quickly a change in state, you're effectively filtering. And so then you can measure, we always knew when we got the standard quantum limit, we would not be in a ground state, but we would have the resolution to measure between a phonon, a single phonon resolution.
Right. Yeah, no, I think that would work just as well. Like in principle here, you could have a jump between the n equals 11 and the n equals 12 Fock state. That's still a discrete transition, and it's still exactly like the photoelectric effect. So yeah, that would work.
Okay, so that makes it easier.
Yeah.
Okay. Is that a question in the back? No. Then, well, I have one more. I mean, you mentioned about optimizing, and you ended up with like 250 kilograms for LIGO frequencies. Can you give me a brief feeling for how this comes about?
Oh yeah, so the optimal detector mass, I kind of jumped to this a bit. So this is the mass. We calculated the detector mass that would maximize the probability that a transition to the n equals 1 Fock state has occurred. Because then if you transition to the n equals 1 Fock state, you can really claim it's a single graviton detection. Whereas if it goes to the n equals 3 Fock state, I mean, you've still detected gravitons, but you've detected 3 gravitons rather than 1 graviton.
And how does this scale if I change like the frequency? I mean,
the optimal detector mass.
Yeah.
So it decays. The exact formula is in the paper. It decays inversely with the frequency.
Okay, thanks. So I think if there are no questions right now, we will now have Nick's talk, who will argue that this is not so easy. Maybe let's thank German again.